Let's take a look at the parametric form of the hyperbola there. So there's random point on the hyperbola. Once again, I'm going to draw in that auxiliary circle. X squared plus y squared equals a squared. Because again, it all comes down to the auxiliary angle. But this time, when I drop the vertical down, now obviously it doesn't intersect the circle anywhere or something like that. But where it hits the x-axis, I then draw a tangent into the circle. So we still get that angle theta at the centre. Now, I could draw an ellipse inside the circle, but now I've got a way of drawing a hyperbola outside the circle. The x value would be the hypotenuse of that right angled triangle. So we can work that out. And again, the radius is a. So x over a would be the secant of theta. So we get x equals a sec theta. Well, how do we get the y value? We sort of force this one because we know the equation of the hyperbola. So if I substitute it in, then I can work out what the y parameter has to be for this to work. So if I sub it in, I get y is b tan theta in order for this to work. So that gives us our parametrics. X is a sec theta, y is b tan theta. Okay, look, I'm not going to go through and derive them all, but we'll see exactly the same as we saw with the ellipse, and that is that the equations will mimic the equation of the hyperbola itself. So the tangent, we'll see x1x on a squared minus y1y on b squared. We would flip the coefficient of x and change the sign in the middle. So it becomes a squared x on x1 plus b squared y on y1. On the right hand side, do you remember with the ellipse we had a squared minus b squared? With the hyperbola we end up with a squared plus b squared, which once again is equal to a squared e squared, same as we saw with the ellipse. And if we sub in the parametrics, we get x sec theta on a minus y tan theta on b for the tangent, and then there's our normal. Okay. Oh yes. I say reminder, but we haven't actually differentiated sec yet, have we? We did sine, cos and tan. The derivative of sec is sec tan. When you differentiate the secant, again the derivative will go at the front, but then it's times sec tan. Tan, of course, we've seen, that goes to sec squared. So that'll come in handy if we're differentiating the parametrics. Now the chord of contact, once again, it will mimic the equation of the hyperbola. So we'll see something like that. X naught x on a squared minus y naught y on b squared is equal to 1. That's all I really got to say, because other than that, it's really exactly the same as the ellipse. All the same sorts of questions you'll see and things like that.